The Autonomous Operating System, the AOS, model-based plug-and-play autonomy for robots in partially observable probabilistic domains with noisy sensing, a research of Or Wertheim and Dan Suissa under the supervision of Professor Ronen Brafman. Motivation. An increasingly wide range of robot skills is currently available. How can an autonomous robot use them to perform tasks? The current state of the art is to use handwritten scripts or state machines to schedule skills into effective behaviors. The challenge is that scripts or state machines are non-optimal, hard to maintain upon environment change or robot skill upgrade. The solution is to use AI planning algorithms to control the robot. The problem is it requires AI expert and a significant integration effort. Our goal is to provide plug-and-play task-level autonomy for robotics. Our solution, the Autonomous Operating System, the AOS, which offers several advantages. Conceptually, we provide full POMDP support with stochastic actions, partial informations, noisy sensing, complex goal, and optimized behavior while balancing trade-offs. We offer an abstraction mapping, which is an explicit and principal mapping between the skill model and skill code. We use generative POMDP models that are based on probabilistic programming language constructs. It offers greater expressive power, easier to specify, and enables much faster sampling rates. Generically, we provide a true plug-and-play system. Given properly documented skill code, no additional programming effort is needed. Documented skills can be added incrementally and used by the system. The AOS uses reinforcement learning to auto-generate MDP heuristics of POMDP solvers. The system has a GUI to visualize the robot belief state distribution and understand the robot's behavior. So how do we use the AOS to develop an autonomous robot? The first step is implementing basic robot skills like navigation, object detection, or arm manipulation. These are out of the system scope. The next step is documenting the skills and environment. An environment file is used to specify the skill-independent aspects of the model. These include state variables, terminal states, initial belief, and state-dependent rewards. Each skill is documented using an SD and an AM file. Semantically, the SD specifies a fragment of a POMDP associated with a specific skill. It describes the expected high-level impact of applying the skill, how state variable values change, the associated reward or cost of the skill, and the information the skill will supply. In POMDPs, these are called the transition, reward, and observation models. The AM file connects the more abstract model of the skill with the skill code. It specifies how to activate the skill code and how to translate skill code execution, including code return value and public information, such as ROS topics, to an observation corresponding to the model. We will now overview a few experiments. In the first experiment, we implement a tic-tac-toe playing robot using our lab's Panda robotic arm. This experiment emphasized the system's plug-and-play capabilities and the advantage over manual scripts and state machines. In the left video, we see a robot playing a regular tic-tac-toe game, which can be easily implemented using a script. In the center video, we are handling a faulty arm that succeeds 50% of the time it tries to mark the center cell. If it fails, the turn passes to the human. Changing the draw skill documentation was easy, but updating a script to reason about probabilistic effects is not trivial. In the right video, we changed the game so that marking cells adjacent to a marked corner cell rewards a player with a point. We only changed the EF file reward model, yet writing a script to win such a game is not trivial. We will now overview a part of an experiment involving a simulated armadillo robot, a mobile base with an arm, to test how the generated policy is sensitive to the POMDP model given partial observability, noisy sensing, and stochastic effects. The simulation environment included a room with two tables, each with a can on it, and a corridor with a person. One can is very difficult to pick. Its true height is 10% of what the robot perceives. The robot starts near the table with a difficult can. Its goal is to give the can to the person. We implemented 3 skills: pick can, navigate to a person or a table, and serve a can to a person. In the left video, we see the behavior of a rough model that assumes that the probability of successful pick is independent of the selected table. Since the pick observation is quite noisy, the robot serves the can, but then because it has no feedback, goes back to the table and tries to repeat the process. In the center video, we see the armadillo after adding an observation skill that more accurately reports if the arm is holding the cup. With sensing, the robot verifies success, and only if the result is yes, does it serve the can and stops. In the right video, we see a finer model in which peak success probability is conditioned on the robot position. The robot first moves to the other table, where the peak is more likely to succeed. In the last experiment, the toy collection domain, we can visually understand the advantage of maintaining a belief state. Unlike classical planning or MDPs that only maintain a single current state. In the left video, we see a TotalBot 3 gazebo simulation. In the right video, we see the AOS GUI that visualizes the robot's current belief state. The GUI displays graphs to visualize the belief state value distribution for each variable. These graphs can be filtered to focus on the interesting variables. Additionally, a generated image displays the belief state, and the color intensity demonstrates a higher probability. Furthermore, the GUI displays the previous action, the observation received after applying it, and the next observation. In this experiment, a robot receives a reward for bringing toys to a child. The toy's location and values are unknown to the robot, yet some prior knowledge is given for the initial belief. The robot has a navigation skill that may fail and has noisy report for its success. The pick skill can only be used 6 times, and it only works if the robot is near the exact toy it tried to pick, yet it receives an accurate observation of the pick success. In the GUI image, the rows are used for information relevant to toys and the robot, while the column mark location as well as the value of the toys. This example emphasizes the advantage of using the POMDP model and maintaining a belief state distribution. Looking at the uncertainty encapsulated in the belief state, how can we expect an AI solver to handle a partially observable domain so common in robotics without maintaining a belief state? A classical or an MDP solver is not expected to supply optimal behavior for such domains. We can see that toy 1, the green toy, has the highest value and is most likely to be at location 2. So an AI planning algorithm will likely try to pick it first, as we can see. Navigating to location 1 adds some uncertainty regarding the robot's location. After receiving the successful peak observation, we have full certainty regarding the toy and robot's location. It will be challenging for an engineer to handle these belief updates manually and reason about which skills to activate in a script. Thank you for listening. We hope you enjoyed the video and are interested in our system. The amount of information we can supply in 5 minutes is limited. Please read our paper. You can use the left QR code to visit our GitHub or the right one to see the extended version of the video with documentation examples.